So Module 6 is on Faraday's law and magnetic induction. And so let's start off with first defining a problem with magnetic flux in it. So we have a magnetic field of 0.055 Tesla. So let me go through and we'll grab everything as we go. So magnetic field, that's B, 0.055 Tesla, passes through a circular ring with a radius of 2.1 centimeters. And remember, as we write down the numbers, we should automatically convert them to the correct SI unit. So that's 2.1 times 10 to the minus 2 meters at an angle of 12 degrees with the normal. And we want to find the magnitude of the magnetic flux through the ring. So flux, remember, we have the symbol phi, capital Phi. And sometimes we put a B on it to say it's magnetic flux. There's also electric flux, which we did not talk about in the first module. Okay, so I want to find the magnetic flux, and my equation is that the magnetic flux is equal to the magnetic field times the area times the cosine of the angle between the magnetic field and the normal to the loop. So here we have a loop that's circular. The normal comes out, let me draw it dashed, comes out perpendicular to the loop, and we're told that the magnetic field is at an angle of 12 degrees to that. So the magnetic flux, which is sort of a measurement of how many of these magnetic field lines are going through the loop, depends on the angle between the normal and the magnetic field. So in this problem, we're told the angle with the normal, so we're good. If we had been told that it was an angle of 12 degrees with the plane of the loop, then that would mean, let me draw it in a different color, that the angle would be something more like that. And I would have to do a calculation. What's the angle from the normal? I would have had to do 90 minus 12 to give me that bigger angle. Okay, but here we're just told the angle with respect to the normal, so we don't have to do anything. Just want to warn you, read the problem carefully so you know whether the angle they give you is with respect to the normal or whether it's with respect to the plane of the loop. All right, so what do we have? We've got B, we've got theta, and we're given the radius, so we can find the area. Remember, area for a circle is pi r squared. So we're going to have to plug that in, pi times 0.021, 2.1 times 10 to the minus 2 squared. And I get a small area, 1.385 times 10 to the minus 3 meters squared. So now I can put that into the equation. So the magnetic flux is B, A cos theta. So B is 0.055 Tesla. Area 1.385 times 10 to the minus 3 meters squared. And the cosine of 12 degrees. And when I throw all that into my calculator, I get 7.45 times 10 to the minus 5. And let's see, I've got two significant figures and all those numbers there, so I got to round that to 2. Let's say 7.5 times 10 to the minus 5. And the units are Teslas times meters squared, which is a Weber. Capital W, small b. I would also accept the units of Tesla meters squared. Okay, so that one was pretty much just plug and chug. All we had to do was find the area. Let's do another one now involving induced EMF. So the induced EMF, remember, is equal to minus, that just gives the direction, the number of turns times the rate of change. So the change of the magnetic flux divided by the change in time. So let's see what we've got here. So I've got a 0.25 Tesla magnetic field. So B is equal to 0.25 Tesla. Is perpendicular to a circular loop of wire. I'll come back to that in a minute to get the angle, with 50 turns. So 50 turns, that's my N. And a radius of 15 centimeters. So I got to turn that into meters. So divide by 100, 0.15 meters. And then I'm going to reduce the magnetic field to 0 in 0.12 seconds. So our initial magnetic field is 0.25. Our final magnetic field is 0. And the time that it takes, delta t, is 0.12 seconds. Okay, so what do we have? Remember, flux is B A cosine of theta. So I've got my B initial and B final, so I can have two of those. The area, I'm given the radius, so I can find the area like I just did in problem 1, so I can get that. Do I have the angle? Well, it tells me something. It tells me that it's perpendicular to the loop of wire. So if I draw, there's my loop of wire, it tells me that B, let me draw the B in blue, is perpendicular to the loop. So my B is going up through the loop. What direction is the normal? Well, the normal, if I draw this dashed arrow, normal is also perpendicular to the loop. So the angle between B and the perpendicular, since they're parallel to each other, the angle is just 0. Okay, so theta is equal to 0. So I've got my theta as well. All right, so let's calculate the area. Area is pi r squared. So that's pi times 0.15 squared. And I get 7.0686 times 10 to the minus 2 meters squared. Okay, so I need to get my change in flux. So I've got my delta T, I've got my N in the EMF. I need to find what's my change in flux. So to do that delta flux, remember delta means change. So that's going to be the final minus the initial. So I need to calculate what it is at the end and what it is at the beginning and subtract those. All right, so phi initial is going to be initial field times the area times the cosine of theta. So that's going to be initial field is 0.25, my area 7.0686, and let's see, I wrote that wrong up there, didn't I? That should be times 10 to the minus 2. All right, and cosine of 0 is 1. All right, so if I put that in, I get 1.767 times 10 to the minus 2 Webers. Phi final is B final A cosine of theta. And in some problems, you might have the B stay the same and the area change. So in that case, you do A initial and A final, and the two B's would be the same. Or you might have the angle change, and in that case, you do theta final and theta initial and have B and A the same. So it's going to depend on the problem, but the steps are the same. So B final is 0. So it's 0. So 0 times anything is 0. So I don't really need to spend the time writing this, but let's go ahead and do it. All right, so 0. So my final flux is 0. So if I go ahead and do the calculation now, let me move that up. Delta phi is going to be phi final minus phi initial. So that's 0 minus 1.767 times 10 to the minus 2. So it's negative 1.767 times 10 to the minus 2 Webers. All right, so now I'm finally ready to plug it in to my equation for the EMF up the top. So EMF is equal to minus the number of turns times the change in flux over the change in time. So that's minus, the number of turns is 50. The change in flux is minus 1.767 times 10 to the minus 2. And delta T is 0.12 seconds. Okay. So if I put that in my calculator, you can see I've got two negatives, so I'm going to end up with a positive voltage. So I get plus 7.36 volts. And let's see, I've got 2 significant figures on everything up there, so let's round that to 7.4 volts as my final answer.